Okay, so today's objective is I can compare two linear functions. So my learner's question is going to be, how can I compare two linear functions? Okay, so this first thing says the graphs of two linear functions blank if the functions have different rates of change. Okay, so if you look at this right here, this is called an intersection. Okay, so they intersect if the functions have different rates of change. So let's find these rates of change. Okay, so I have this point here and this one here. So up 2 over 2, well, 2 divided by 2 is just 1. And then the rate of change of this one is here to here. So up 1, left 4. So that would be negative 1/4. Okay, because I go up 1 and then negative 4. Okay, so those are different rates of change. So they intersect each other. And next topic, we're going to be doing systems of equations, where I'll give you two equations and then we'll use different methods to find where they intersect, which is something like that. Okay, now we have this second one, and this time on this one we noticed, or I noticed, that one's positive and one's negative. Okay, so they're definitely going to intersect. Whereas over here, these are both positive, but you look, they still intersect with each other. Okay, so my rate of change for this one goes from here to here, so up 1, right 3, so 1/3. And then this one, those are my 2 points I'm using to find the rate of change, up 2 over 1, so that's just 2. So again, they're both positive, but they're different, so they intersect. Okay? So that's one way that they can compare to each other. Even if they have different rates of change, that's what ends up happening. Okay, so we're going to be looking at different representations of functions and equations and making some conclusions based on some information we can gain. Okay, so example number 1 says the number of words y you can type in x minutes can be represented by the equation y equals 55x. The number of words your friend can type in x minutes is modeled by the graph. Which of you can type faster? Okay, so me, I'm y equals 55x. So how many words per minute do you think I can type? Okay, 55. So I can type 55 words per minute. Okay, now we have to find out how much our friend can do. Okay, so this is a proportional relationship. Okay, so I am just looking for that constant of proportionality. Okay, or my rate of change. Remember, with constant of proportionality, I can just do y over x. Okay, so here's a point on there. My y is 150, and my x is 3. Remember, I'm only able to do this because it goes through 0, 0. Okay, that makes it proportional. Okay, so 150 divided by 3 is 50. So my friend can type 50 words per minute. So now I just compare those two, and I can type faster. Okay? Okay, go ahead and do the U try. It's about a train, car and a train. Okay, example number 2. For each city, there is a linear function that describes the temperature in degrees Fahrenheit in terms of the number of hours since 8 a.m. Which function has the greatest rate of change? What does that mean in this situation? Okay, so we need to figure out the rate of change of each. Okay, so Eastbury, so we have Eastbury, Topperville, and Hilltown. Okay, so it says at 8 a.m. the temperature was 62 degrees Fahrenheit. Between 8 and noon, the temperature increased by 3 degrees Fahrenheit per hour. Okay, so that means that the rate of change for Eastbury is 3 degrees per hour. Okay, then we have Topperville. Topperville, it says T equals 54 plus 2h, where T is the temperature in degrees Fahrenheit and H is the number of hours since 8 a.m. Okay, so if I look here, I'm looking for the rate of change. Remember, my rate of change goes right before my variable. So this would be 2 degrees per hour per Topperville. And then there's Hilltown. Okay, Hilltown's is from 6 to noon. Okay, so I'm just going to find, this is per hour. Okay, so all I have to do is find the temperature change, and it looks like it increases by 2 each hour. Okay, so Hilltown is 2 degrees per hour. Okay, so Eastbury has the highest or largest or greatest, let's use the word greatest rate of change. Okay, so remember that triangle just means change. Okay, it says, what does that mean in this situation? So for this situation, it's talking about degrees per hour. So that means, so I'm going to say which means its temperature is increasing the fastest. Okay, so we always want to take it back and relate it to the label on my number, on that rate of change, so that I know exactly what we're talking about. We're not talking about money here, we're talking about how fast the temperature is increasing. And this is 3 is more than 2. Both of them. Okay? Okay, go ahead and do the try number 2. Okay, example number 3. So it's the same, same 3 cities we were looking at before, but now it's asking us to compare the initial values and what that means in this situation. Okay, so for Eastbury, Eastbury's starting temperature was 62 degrees. Okay, Topperville's starting temperature was that 54 degrees. Remember, the 2 was the rate of change, so the 54 is the temperature. Or, yeah, is that starting temperature. Okay, and then Hilltown started at 58 degrees. Okay, because it's literally right there on there. Okay. And actually, I think we need to change this one, because these are all 8 a.m. Okay, so we actually need to start here for Topperville. Okay, or for Hilltown, I'm sorry. Okay, because these are all since 8 a.m. So we're looking at 8 a.m. Okay, so it wants us to compare the initial values. Okay, so Eastbury and Hilltown have the same initial value of 62 degrees, which is more than Topperville's. And then it also wants to say, what do those initial values mean? Okay, well, that was their starting temperature. Okay, the initial values here represent the starting temps. Well, what time was this starting at? Okay, it was starting at 8 a.m. Okay, represent the temps at 8 a.m. So we're doing that specific time, okay, because that's our T equals 0 is the 8 a.m. Okay. Okay, go ahead and do this try right here. Okay, so here's a summary, okay. So right here, we're going to look at both the rates of change and the initial values. So do my initial values, are they the same or are they different? They're different. Okay, and then are my rates of change the same or are they different? They're different. Okay, so this is different rate of change, different initial value. They cross, they intersect, okay? They intersect at one point, okay? Okay, well then you have these two, okay? Let's look at our rates of change. Okay, are their rates of change the same or different? They're different, so different rate of change or different slope. Remember, slope and rate of change are the same thing. Slope is just more specific to linear. Okay, now do they have the same y-intercept or different? They have the same. Okay, so they have the same y-intercept, which means instead of intersecting at some point we don't know, if they have the same y-intercept, that's where they're going to intersect. Okay, so intersect at y-intercept. So that makes it really easy to tell when they're equal, when they're the same. Okay, okay, then I have this one down here. Let's see, do they have the same rate of change or the different rate of change? These ones actually have the same rate of change. Okay, do they have the same y value or different y values? Okay, so there's my y value, there's my y value. Those are different. Okay, different y-intercept. Okay, which means, what do you notice? They don't ever cross. Do you remember what that's called when they don't ever cross? That's parallel. Okay, so lines are parallel, never intersect. Okay, so remember back at the beginning we said the graphs of two linear functions intersect if the functions have different rates of change. Okay, the different rates of change is what creates these two up here. Okay, whereas down here, okay, when they have the same rate of change, they're parallel and they never intersect. Okay. Okay, that's it for today.